1 2 1 1 2 1 2 1 2 1 2 1 2 1 2 1 2. So this is the relativistic slide rule. These are the constants that I'm using, speed of light, and that's how I'm converting L to meters and T to seconds. Planck length, gravitational constant, Coulomb's constant, fine structure constant. I put in a value for beta for the Earth, and for hydrogen, radius of hydrogen and the radius of proton. So that's how I'm graphing it using these. And there are only three base units. L, that's the Lorentz transform. T is just the usual velocity, is distance over time, and for all the constants 1. And then beta is L over T, represents velocity over the speed of light, the ratio, and in electromagnetic terms it's the magnetic vector potential. So this is it moving. It's the yellow line. Now the yellow line's getting longer and longer and longer, and the yellow line is getting up to the speed of light there. So I'm going to drop it down to 0.6, and I'm going to show how the twin paradox is resolved. So to do that, I also use a scalar. I'm just going to set that to 1. So 1 light year. Now, at a velocity of 0.6, constant velocity that is, the distance for light according to Bob is 0.8, which is L, and I'm going to have to split the screen and get something that I can draw on. That'll do. So where are these things? Well, for a start, the constant is that length there, so that's 1. That's also 1. L is that length there, because that's the velocity there. Velocity is L over T, and so obviously you're wondering where T is. Turns out T is that length there, and everything else I do is just based on these 3 base units. You can see that there's all kinds of things going on. This little length here is actually L cubed over T squared, which is GM or KE, depending on whether you're working with the electromagnetic field or the gravitational field. And in the twin paradox, the distance according to Bob from Earth to, say, Alpha Centauri, it's going to be 0.8 of what it is for Alice. So there is the simplest resolution to the paradox is that according to Alice, Bob's frame is contracted, but that just means that his spaceship is only 0.8 of its original length, and that's not going to make any difference at all to how long it takes him to get from Earth to Alpha Centauri, according to her. Whereas for Bob, his ship's the normal length, 1, but the other frame is 0.8, just like for Alice, except that means that the distance from Earth to Alpha Centauri is 0.8, because that's Alice's frame. So in other words, Bob's frame is inside Alice's frame, and so it's going to take him a lot less time to get there. If the distance is only 0.8, it's only going to take him this much time to get there, which is t, whereas according to Alice it's going to take this much time, which is t over l. T over l is obviously gamma times t, and gamma is actually that length from there to there, and that'll do. That's the resolution with respect to space. There's another resolution with respect to time, but that's easy to demonstrate too, but I'll do it in the next one. Okay, bye.